All right, so here's what we got today. I think I've mentioned this. I broke the assignments for this section on linear approximations. I broke them into 3 parts. First one was the stuff I covered in the video on Tuesday. This is the middle one. This is on what we call differentials. This is kind of the smallest of the 3, and then the last one's going to be on some applications of this. So let's talk differentials here. Remember that what we were doing in the last video, we were using linear approximations to estimate some function values, right? And I ended up with some like square roots and things like that. How's that coming? Do we need to go through another example of that? How is that stuff? Is it so? I mean, have people started that one yet? Okay, let's maybe do one quick example of that before we jump into this stuff. Okay, what if we wanted to, for example, let's say, what if we wanted to estimate, what's that?
I must say, I love the birthday socks.
Do you like? I've got a injured Achilles tendon, and these help so much if I wear these things. So, yeah, we are. I know. We're kind of not the most robust stock, I guess. So let's see. We've got. There we go. Now it's working. Okay, what if we want to estimate something like, how about, let's do e to the 0.1. Okay. How could I do that? How could I do that? We're using a linear approximation or a linearization, right? What do you think? Say it again. Okay, yeah. So what's a value close to 0.1 that we know how to deal with for e? 0, right? E to the 0 is what? 1. Anything to 0 is 1, right? Okay. Good. So we're going to pick a value close to my input of 0.1, and we're going to come up with just a linear approximation of the function. Essentially, all we're doing is finding a tangent line to the function there, right? Okay. So what did we say about that? Now let's review kind of the concepts we went through. So all we did was we took the point slope form of a line where x1 and y1 are the values of some point that we know, right? Those are actually numbers. So in this case, x1 and y1, we're going to replace those with x is going to be 0 and y1 is going to be the output at 0. And we just turned this into, we just solved for y. And that's really all we did. But we didn't call it x1 and y1 and m. We gave them some different names, right? We said that the value, what do we call the value close to, the convenient value close to our input? We called that a, didn't we, right? So we're going to replace the x sub 1 with an a. And what gives us the slope of the tangent to the curve? Like if I were going to draw a picture of this, it would just look like this, right? I've got this exponential curve that's doing that, and we know it goes through the point 0, 1, right? We're trying to estimate the value of this thing at 0.1, so it's going to be, really close to that point, right? Very close to it. We're just trying to use a tangent to the curve right here, though. We're just going to use that tangent line to approximate the curve in the vicinity of x equals 0, right? Okay, so we're talking about a tangent line. That's our linear approximation. What gives us the slope of the tangent line then? I think say it again. Yeah, okay, good. The derivative of the function at that point, right? That's telling us the slope of the tangent. So this is just becoming f prime of a, and what's y1 being replaced by? Right, that's the y coordinate of our point that we know, f of a. Right, good. Just the value of the function at our convenient x value. So remember, this was, and we ended up giving this some fancy name. Instead of calling it y, we called it L of x. So that's just our linearization, isn't it, right? It's the same every time. It's just a linear approximation of the function, okay? So all we'd have to do here is just plug in, there's the template. Now we have to just plug in the specifics for this example. Okay, so what's our function in this case? What's the function that we're plugging values into? The input is 0.1, e to the x, right? We're just plugging in an x value into e to the x. So we've got f of x equals e to the x. So then we can calculate a derivative. What's f prime of x? E to the x. And we know a is 0, so we could calculate f of 0 equals e to the 0, which is 1. F prime of 0 equals e to the 0, in this case, same thing, which is 1. And we've got everything we need for our linear approximation then, right? L of x is equal to f of a, we said was 1, plus f prime, which is 1, times the quantity x minus a is 0. So we just get the simple line 1 plus x, right? That's it. That's our approximation to the curve. So then if we want to evaluate this at, what are we doing, 0.1, I think it is. So L of 0.1 is just equal to 1 plus 0.1 equals 1.1. Okay, makes sense? All right. So that's really, as you work through that first assignment, I mean, that's all it is. It's just repeated applications of that same concept, just using calculus to give us, quickly and easily, to give us the equation of a tangent line to a curve at a point that's close to some input value we're interested in plugging into our function, right? And it's just an approximation, but it's a lot easier sometimes than having to calculate the exact value. Okay, so in addition to estimating function values, linear approximations can also be used to estimate the change in a function's output for small changes in the input value, okay? So this is a topic we call differentials. Differentials provide a means of easily estimating the function's response to small input changes. So if I've got some function, if I want to just tweak the function slightly, if I want to move it very slightly along the x-axis, if I want to change the input very slightly, what is going to be the change in the output, right? Well, we can make an estimation by using that same concept of just a linear approximation, right? Instead of, like, if we were, well, I got some pictures in a second we'll look at that'll illustrate that a little bit better. So before we get there, though, differentials end up being very simple for us to calculate. They're actually just different forms of derivatives that you already know, right? So all we have to do is rewrite the traditional, it's called Leibniz derivative notation. That's what we're used to, dy dx. That's what we call Leibniz notation, or just quotient notation. All we're going to do is we're going to slightly change the way we write our derivatives. This is a true statement, right? Dy dx equals f prime of x. They're just different ways of saying the same thing. dy dx means the change in y over the change in x is just equal to the derivative, f prime of x. Well, what if algebraically I just multiply both sides of that equation by dx? Don't I just end up with dy equals f prime of x dx? We didn't do anything substantial, right? But this is what we call differential notation, okay? When we write it in instead of writing it as dy dx, we just write it as dy, okay? So let's just see what we get. I mean, just to prove my point, you guys already know the answers to all these blanks you can fill in, right? We're just gonna take some functions that we've already dealt with in the past that we already know how to differentiate, and we're just gonna write the answers using differential notation instead of the notation we have been using. So y equals tangent x. So what do you suppose dy is then? Dy is always just gonna be the same derivative you always take times dx. If x is the variable of differentiation, x is the input here, right? So we're differentiating with respect to x. So whatever we're differentiating with respect to, we're just going to multiply by d that at the end. That's it. So what is the derivative of tangent x? Secant squared x. So if I want to write this in differential notation, all this is secant squared x dx. Big deal. That's it. We didn't really change anything. Just a different way of writing it. Okay, how about this one? This is a chain rule problem, right? So let's go through this one. If f of x is sine squared of the quantity x cubed plus 1, this is some good chain rule practice. What's our derivative going to be? Okay, so we got to work our way, we got to work our way in from the outside, right? What's the outermost function here? What's the first thing that's being done? Everybody agree it's being squared first? If I do sine squared of hand, what that really means is sine of hand squared. Right? That's just shorthand notation. But the exponent is what we're doing first. We're squaring it first. Then we're taking a sine, right? And we're taking a sine of that stuff, that polynomial, okay? So the first link in the chain is going to be, what's it going to be? Yeah, everybody get that? Because we've got a sine that's being squared, and so the derivative of hand squared, and that's really all that is just, well, I guess I wrote the answer out. Maybe I wrote the whole thing simplified. Let's just do it this way. It's equal to 2 times hand to the 1, and hand is just sine of x cubed plus 1, right? Okay, next link. What's the next link in the chain going to be? Once we've taken care of the squared, what's the next function we encounter when we move one layer inward? Sine. Okay, derivative of sine hand is cosine hand. I don't need that 1 there, do I? Get rid of that. Times cosine of whatever the hand is there, x cubed plus 1. Okay, so we work inside the sine, and then we've got the innermost layer. What's the derivative of the inside layer? 3x squared. Derivative of x cubed plus 1 is going to give us a 3x squared. And so if I just simplify all that stuff, 2 times 3x squared is 6x squared times sine of x cubed plus 1 times cosine of the same thing, dx. I can't forget the dx at the end because I'm writing this in differential notation, okay? How about the bottom one? So here now, finally, we're looking at maybe a different kind of function. This time, previously, our input was always x, right? And our output was whatever the function was. Y, we called it y in this case. We called it f in this case, right? F of x. What about that bottom one? What's my input? R. Output. Volume. Okay. So I'm calculating dv. What am I going to stick at the end of this thing? What's going to be at the end of this thing? Everybody agree? It's going to be a dr. It's going to be a regular derivative, but then times dr. So we're just going to get, if I bring the 3 down, 3 times 4/3 is just 4 times pi times r squared times dr. That's it. Okay. Okay, why do we do this? Well, here's what this represents, right? If you think about this function, the black, this is one that we looked at previously. The black, it's actually a curve. You just can't see it, that it's a curve very obviously because we're zoomed in. But the black curve is the function, and the blue line is the tangent to the curve, right? So in traveling from this point to this point on the curve, the y value has changed, right? So what we really should do, this, I'm going to make one little change here to this. Let me cross that out. So we could say here that the amount that the function is actually changed is what we could call delta y. How much did the function change when x changed by some certain amount that we could call delta x? We could calculate that, right? If we started at an x value of 2 and we ended up at an x value of 2.1, delta y is always going to equal the same thing. It's just going to equal, in this case, it's going to equal f of 2.1 minus f of 2, isn't it? Everybody agree? We're just trying to calculate what's the function value here minus what's the function value or the y value here to find the difference. Okay? That's the exact value, but sometimes that might be tough to calculate, tough to compute, right? If it's a really kind of a bad looking function with lots of exponents or logs or who knows. Sometimes they're tough to evaluate. So instead, we're going to use the same concept we did before. We're just going to use this tangent to the curve, and we're going to estimate the actual change in the function by the change in the linear approximation of the function. How much did that change, right? So we're going to call this change from this value down to the estimated y value. It's not the exact y value, the estimated y value at 2.1. We're going to call that dy, okay? And that's really the meaning of a differential, right? Think about this now. We've got this slope triangle we've created. Here's dy. We're going to call this dx, right? That's just a slope, isn't it? The definition of slope is rise over run. So the slope of the tangent line is dy divided by dx, right? Rise over run. It's also, as we know, it's also equal to how did we get the tangent line? Well, it's the derivative of the function at 2, correct? That's how we got the line to have that slope. That's what derivatives do for us. So this is just equal to f prime of x, right? So if we just write this in differential notation, dy is the approximate change in the function. That's just equal to f prime of x times dx, right? Okay, so there we have it, right? It's really just a restatement of the stuff we just did, same stuff we just did, but now instead of us trying to find what the value of the function is there, we're just trying to figure out how much it changed. That's all we care about with the differential, is how much did the function change when we move the x value from there to there. What's the approximate change in the function dy? We don't really care about what the actual value is, just how much was it tweaked, okay? So this is what we mean by a differential approximation, right? So if we identify a as a convenient value of x, the actual change in the function in response to a change in the input we're going to say the change in the input, we're going to call that dx, is just this, right? It's f of a plus dx minus f of a, okay? The value of the function at our slightly offset x value minus the original value of the function at the original x value. But sometimes that's tough to calculate. So instead, we just use the approximation. The actual change in the function is approximated by the differential, f prime of a times dx, okay? So these differential approximations, they rely on the initial value of the input, a, okay? The magnitude of the small change of the input, which we're going to call dx, okay? If x is our variable, which usually it is, right? Doesn't always have to be, though. And we need to know the slope of the tangent line, which is just f prime of a. So let's look at an example then. We've got this function, f of x equals x squared plus 3x. Let's make an estimate here of the change in the function's value when we start at 3 and we tweak the x value, we move horizontally by 0.1. Okay? So what do I do? Okay, I'm trying to find, what is it I'm trying to find here, first of all? Well, I guess it tells me right there, doesn't it? Find dy, right? The estimate of the change in the function. What's our definition of a differential? Everybody agree, right? That's all it is, right? The differential is just the derivative times dx. That's all we've done is just multiply both sides by dx. Oops. So let's calculate the derivative first of all, right? We know the function's x squared plus 3x. The derivative is just 2x plus 3. And here's our differential, right? dy is just f prime of whatever convenient value we're going to use, which in this case is 3. Okay, so it's going to be f prime of 3 times dx. The amount that we're changing the function, we're changing the x value. Okay, so we can do that. What's f prime of 3 is just 2 times 3 plus 3. Right, so that's giving us 9 times dx. How much are we tweaking the x value? 0.1. And so we get an estimate of 0.9. That's approximately how much the function is going to change when we tweak the x value, starts at 3, and we change it by 0.1. That's it. That's all a differential is, just an estimate in the change in the function. Okay, so it's approximately 0.9. When we compare it to the actual value, it changes from 18 to 18.9. It looks like the actual change in the function is 0.91. So we're pretty close, right? Pretty close. Why are we pretty close? Well, you can see right there. Because the tangent line is a good approximation of the curve close to x equals 3. Yes, sir? To the 9. Okay, so what did we do there? All we did was what's our value of a? Maybe that's what I ought to plug in. Our value of a is just 3, right? So this is just f prime of 3. There's f prime of x. So f prime of 3 would just be 2 times 3 plus 3. That's how we're getting that, okay? All right, let's try another one. Okay, how about this one? Okay, so we're starting, we want to know when x changes from a value of 3, it changes by an amount 0.1, we want to estimate what's the function's response going to be. How much does the function change? Okay? All right, so we have to identify, let's take our derivative. First of all, we're going to need the derivative, right? So would everybody agree the derivative of cosine hand is just minus sine hand times the derivative of hand would just be pi in this case? We'll just put the pi out front. So negative pi sine pi x. Okay, well then we know that dy, in general, dy is always just f prime of a times dx. Well, what's our a value this time? Everybody? Show me fingers. What's our a value? Yeah, it's just 3, isn't it? Right, that's what we're starting with. So that's a. And the amount that we're tweaking at dx is 0.1. So then we're just calculating f prime of 3 times 0.1 times dx, right? F prime of 3 is just going to be negative pi times sine of 3 pi. What's sine of 3 pi? So there's 0, pi, 2 pi, 3 pi. 0, right? So that's going to give us pi times 0. So that's just 0 times 0.1, 0. Right? So the estimated change in the function is 0. What is it actually? It's going to be close. It's actually, instead of being 0, it's, well, whatever 1 minus 0.9511 is. Right? So it's less than a tenth. Okay? Everybody see that? So it's a good estimate. Right? Okay, why do we use this? What's the big deal? Well, one of the things this does for us is it's a good way for us to estimate like propagated error if we're doing a computation. Like for example, small changes in input, dx, we could use to represent measurement error. Like if I had to measure very precisely, if I were measuring a distance, I could have a really good ruler, but there's going to be some error involved because I'm a human and I'm trying to read this nice calibrated ruler. So say I'm trying to measure something that's 1 meter, it's 1 meter, right? I think I've got this measurement at 1 meter. Well, I might decide if I look at this thing, okay, it's not exact. I can probably get it to within maybe, if I'm really accurate, maybe 1/10 of a millimeter or something, right? So 1,000th of a meter. But there still is that error, right? So if we're using this to maybe build a cube, for example, that's 1 meter on each side, and I want to calculate the volume of that cube, well, the volume theoretically should be 1 times 1 times 1, which is 1 cubic meter, right? But do you see that those small measurement errors are going to propagate? What if I overshot, for example? What if it's actually 1.0001 meters on each of those dimensions? The volume's not going to be 1 meter then, is it? It's going to be slightly bigger than that. You see my point? Or if I undershot, it could be slightly smaller than that. So we want to make an estimate of what's the propagated error going to be. Is it just going to be, we said I could get within 1/1000th of a meter. Is the propagated error going to be 1/1000th of a cubic meter? It's not, is it? Right? Because there's a calculation involved. And so it's going to change the amount. You everybody get that? It's going to change the amount of the calculated error, of the calculated volume. That error is going to be, it's going to be cubed, isn't it? Right? Because we're taking the length and we're cubing it, and so that little bit of error is not going to be linearly translated into the volume. It's going to be changed a little bit, right? So we want to be able to make an estimate of just a quick estimate of, well, what is my propagated error going to be? Okay, so like, what's my example here? Okay, I won't mess with that for a second. Let's take a cube right here. Let's take this cube example. Cube whose side length is 5 centimeters. We can measure, not calculate, we can measure the length with an accuracy of plus or minus 0.1 centimeters, right? Okay, if I wanted to calculate the exact propagated air, well, then I'd have to calculate what's my volume when I input 5 centimeters minus my volume at 5.1 centimeters. I'll take the absolute value of that, so I always make it positive. And I could also do the volume at 5 minus the volume if I were inputting 4.9 for the length of each side. And then I have to see whichever one is bigger. Well, that's a lot of work, right? I got to make, that's a lot of stuff to do. Instead, we could just make an estimation of the propagated air by saying, okay, well, if we're going to say that dx is the measurement air in length, then dv is just going to be the amount that impacts the calculated volume. So that's my propagated air. Okay, give me thumbs up, thumbs down, thumbs sideways on that. Okay, so let's go back and look at an example. What if we look at like this example right here? What if the black function is actually a volume function? Okay, so let's say that we're inputting some kind of a length measurement, and where the black function is like volume of a sphere would just be 4/3 pi r cubed or something, right? Okay. We want to know if I think I'm shooting for a measurement of 3, but let's say that the error is plus or minus 0.1. It might actually be 3.1 in that case, right? We want to know if the measured value creeps from my hopeful value of 3 up to this different value, this error-prone value of 3.1, how is that going to estimate, or how's that going to change the calculation that I make? The calculation that I make for the output was 18 in this case. Pretend that's a volume, okay? So pretend I'm calculating a volume of 18. If my measurement is off by 0.1, it's going to change my calculated volume by how much? Well, in this case, it's changing it by 0.9, right? The volume that I'm calculating could be as much as 0.9 off the actual, see what I'm saying? The volume that I'm targeting, okay? So this would represent, instead of dy, this is representing dv in this case. We're using the differential to just estimate how much is it going to change the calculated volume that I'm computing from these measurements of length that have an error built into them. Okay, so what about this example then? So if I know that I'm calculating the volume of a cube, well, that function is just v equals x cubed, right? So v prime would just be 3x squared, simple derivative. The estimated change in volume is the differential. dv is just going to be v prime of a times d, whatever my input variable is, which is x in this case, times dx. Okay, what's a? What's a? Yeah, it's 5, right? That's my measured value. What's dx? Well, 0.1, right? Because that's the error, okay? So if I plug this in, I know we got to go. If I plug this in, then v prime of 5 is just going to be 3 times 5 squared. That's just 75, right? Times plus or minus 0.1 is giving me plus or minus 7.5 cubic centimeters. That's pretty cool. That just estimated the propagated air that I'm going to get my volume calculation, okay? All right, we'll hit this again next time.